Welcome to session number 23 in the series Analog Circuit Design using ADS. My name is Anurag Nigam, and in this session I am going to continue on some of the applications of op-amps, right? So op-amps and OTAs. So last time I designed a component for a OTA. There were two variants of a OTA. One was a high gain but low bandwidth, and the other is a slightly larger, so slightly larger bandwidth, and these two simulated like this. One of them has a bandwidth of around 11 megahertz and a gain of around 47 dB. The other one has a gain uh, of 39 dB and a bandwidth of 38 megahertz. Now both of these, right, they don't have an output stage, so if you want to use them in feedbacks, resistive feedbacks, you won't be able to use them. So if you look at OTA1, for example, we made a component of it, right? So let's look at OTA1. So in this case I would have to add here a source follower, right? And that source follower, right, would be a PMOS, because the output here is a NMOS. So there will be a source follower, right? So what I will have is one of these transistors repeated as a mirror to mirror this current, correct? So this is going to mirror that current, so this is going to come from this, and then I'm going to repeat the same transistor as a follower. So in this case I'm going to take this and I am going to have a follower here, right? So now the output will go to that follower, and the output here would be from the source, right? So this VO I will name over here as VO, and I'll simulate that. So what I have done is I have given a source follower stage to a OTA. Okay, this will have slight impact on the performance. Okay, so now what you have is 46.9 gain and 43.9 is roughly over here 10 megahertz bandwidth, right? So this is OTA1. So what I'll do is I'll just take this and put it at the output stage. So edit, copy. So if I go to the component, I am going to have a edit, paste, correct? And in this case my output would be this node, right? So let me just put this follower over here, okay, and this one is driven by that, and this one is grounded, and this pin I am going to attach to the output. So in this case this pin would be connected to this output. Okay, so this is my OTA1. Now same treatment I can give to OTA2. So in case of OTA2, I'm going to copy the same stuff, right? So let me just copy that over here, and then I'm going to just repeat that, okay, over here, and this is going to be the output source follower. Okay, so in this case this is being driven by this one, and this is the output, correct? And here this I will transfer to the output node VO. Okay, so VO, and I'll just simulate that, and then I'll make a component out of this. Okay, so this is another OTA which has 3 dB bandwidth. Okay, so it has a 38 dB gain here, 35, 38, 37, 36, 35. Okay, so basically this will go up to 35 over here. So almost 33.5 megahertz is the bandwidth over here, the first corner frequency, right? So I'm going to use that. So I'll make a component out of this. So OTA2, I'll just copy the cell and I will call it OTA2C. Okay, so this is going to be component, and to make this component I will just throw out these. Okay, and I will leave the common mode. So in this case I am going to just have same grounds, just like I did for the previous one. So this is one ground over here, and these are my inputs. So this is a non-inverting input and this one is a inverting input, right? So I am going to just make sure my grounds are proper. So this is the ground and I'll connect a pin to it, and then I would have this as a VDD. Okay, so I will create a pin VDD here, right? So that's VDD, and then there is a ground pin which is a GND. So that's a ground pin, and then you have this one as a INV, NINV. So this is a NINV and this one is a INV. And then this one is a VO, right? So this is the output pin here. Okay, and I'll remove this name here. So what I have here is a OTA2. I'm keeping the current sources inside because I want the hierarchical design to be cleaner. Okay, so I'm going to make a symbol for that. So what I'll do is I will take a op amp symbol and just copy it over here. So if I go to 3-stage op amp, okay, so this is the op amp, right? So what I want is just these, so I can just copy these, right? So I'll say edit copy, and then I will make a new symbol for OTA. So let's look at OTA-C, new symbol, and create a symbol, say OK, and that's the symbol which I am going to replace by my design there. So I'll say edit paste, that's over here, and I have inverting and non-inverting input. So I'll just copy these pins and these names. I will just mirror them and I'll just place them here, and this is inverting, non-inverting input, this is my output, right? So I will just copy that over here. This is my ground, which is over here, and this is my VDD, which is over here, and this was a current source which I am no longer using. So I'll just delete the remaining stuff. Okay, so this is going to be my OTA2. So I will put in a text here saying that this is a OTA2. OTA2. Okay, so this completes my OTA2. Now what I want to do is I want to make components circuits using these op amps and OTAs. So there I want to do, first thing I want to do here is instrumentation amplifier. Instrumentation, just 1 second. Instrumentation amplifier. Okay, so this instrumentation amplifier, okay, is going to be a circuit like a differential amplifier, but it has got more stages. So for example, we have one op amp which, okay, so this is an inverting input, this is a non-inverting, so this is going to be my V1, right? And then it has this resistance R2, and then this is connected over here, so this has RB, and then I would have another resistance R2 over here, and this is going to another op amp, so this is going to act like an input stage. Okay, so that's another op amp. Here is the inverting, non-inverting, and this one is connected over here, and this is V2, right? Now this is VO1, this is VO2. Now this is given to a difference amplifier. So if you remember, so there is going to be resistances over here, correct? So basically, let's say this is R1 and this is R1, right? And this is going to the inverting input, and this is RF, and this one is R1, right? And I am going to put in a DC VCM from here. So I'm going to put a VCM for this device from here. So this will be VCM. This is my output. So this is called a instrumentation amplifier. And let's simply define the gain. So this one would be V1, right? And this one will be V2. So the current in this RB is going to be V1 minus V2 by RB, correct? So this is the current. So now this current is flowing out of this node, so this is going to be positive, right? So VO1, just okay, let me make sure I'm recording. Yeah, so this would be the current through RB, right? And VO1 would be R2 times of this will be roughly VO1, and VO2, okay, it will be minus of R2 times of, because the current is flowing into the output node, R2 divided by RB times of VO2. So this will be equal to VO2. Now VO1 minus VO2, right? Okay, VO1 minus VO2, okay, this is the differential input, is equal to R2 minus of minus R2 divided by RB, right, times of V1 minus V2. So now this will be approximately twice of R2 by RB times of V1 minus V2. So this is VO1 minus VO2. Now VO, which is the output of this entire thing, is a difference amplifier, so that will be minus of RF upon R1 times of the input VO1 minus VO2. That will be same as twice of R2 by RB times of V1 minus V2. Okay, so now this one is the gain of the instrumentation amplifier, right? So this is the gain of the instrumentation amplifier. So this is what we are going to create here, an instrumentation amplifier, and this is a differential amplifier which is used in number of applications, like bridges and there are lots of measurements based on bridges, right? So this instrumentation amplifier can be used for magnifying very small signals. Second thing is, because it is differential, the common mode noise is going to cancel out, right? So what will happen is that in case of very weak signals where the noise may dominate, you can have a differential signal, so you would be able to cancel out common mode noise. So let's go ahead and make a instrumentation amplifier. Okay, so instrumentation amp1. Okay, so this is instrumentation amp1. Okay, so what I'm going to do is, first I'm going to use a 3-stage op amp. Okay, so this is a 3-stage op amp. So this is one terminal, right? And then I'll just flip it upside down. Okay, so this is going to be my second terminal. And let me move the text. So one is over here. Okay, now I would have I would have 2 resistors. So let's say I go to lump components, I pick up a 100k resistor. So this is going to be 100k. So I'll pick up 2 resistors which are 100k. 100k. Sorry, not over here. Here. So 100k resistors. So this would have a gain of 100 by 1k, right? So let me put here a 1k resistor. So let's just copy this. So that's a 1k resistor, and then I'm going to repeat this to be another 100k resistor. Okay, so now here it's connected here. That's that. And then I have this one connected here, this one connected here. So this has a gain of 200. So which is going to be roughly 43 dB, right? This is going to be 43 dB. Sorry. Okay, so I'm going to put here a VDD. So let's look for a sources frequency domain, and I'm going to pick up a VDD here. So this time what I'm going to do is I'm going to name this. So I'm going to name this as VDD. Okay, and all others I'm going to name VDD. So this is VDD, even this is VDD, right? And I will separate out the ground, so not an issue. Okay, so next I am going to repeat this op amp as another stage over here, right? And again I would have a what you call 1k repeating. So I'll just take 1k here and repeat it out here, and 1k here, over here like this. Sorry, and then I have a connection like this. Okay, with this I am going to have 100k as the RF. So I'm going to have 100k as the RF. So I'll rotate it out here like this, and then I'll have to place one more 100k. Sorry, one more 100k I'll paste for the common mode input, VCM. Okay, so let's put that over here. So this is done. Let's me move this text to the top. So this is done. Next is I'll connect the current sources. Okay, so I'll pick up this source, and this source is pulling out a 20 micron current from here. So this will be 20 micron current pulled out here, right? And this is ground. So this is ground, and you can connect a ground here, correct? And this is F5. I'll move it on that side. That's fine. And the same thing I have to repeat at the bottom. So I'll take this, rotate it, and flip it, and that's it. So this is biased. Now this one also has to be biased, right? So I'm going to take this one and copy, and this is going to be over here. Fine. And the issue is this resistance I'll pull down, right? And here I'll put a VCM. Okay, so this is a feedback. Okay, and then I'll put a DC. So this is supply of 2.4 volts. 2.4 volts, and there is a 1.2 volt common mode voltage. Control C, Control V. So this is going to be, so this is not VDD, so I'll throw this out. This is going to be VCM, correct? And I'm going to generate a VCM variable, and I will call this one as VCM. And this VCM is going to be 1.2 volts. Okay, so now I am going to put in here a signal, right? The two signals are going to be differential, and this will be the output, correct? So I will go to VAC. Okay, and in this case this will be 0.5, right? And this would have a DC value of VCM. Okay, and this will be grounded. So this is my one input, which is a non-inverting input, and this is my inverting input, so which will be 180 degree out of phase. So this will be 180 out of phase. So I'll put here 180. So this gives me a differential input, and this is my common mode. So this is my output, so that I'm going to name as VO. Okay, so basically this completes the instrumentation amplifier. So next what I'm going to do is I'm going to put in here the library include file, right? So I'll go here and pick up the library include file, and then I want to do a AC analysis, right? So okay, escape. Okay, not two of them, so I'll just save it. And what I'll do is whatever OTA response I was seeing, right? So inside op-amp circuit there is a OTA, right? So I'll just copy this controller, edit, copy, and then edit, paste. Okay, so now I am going to hit simulate button. So let me check. So everything is in place, everything is in place, everything looks in place. Only thing is I will display this guy, and I will display this guy. Okay, so everything looks in place. Let's hit simulate, and let's plot the output. So I expect output to be around 83, right? So V out dB, and here I am going to put a log scale on x-axis, and I will put here a marker. Okay, so this is a 83 dB gain, as you expect. Why? Because 200 is the gain on the first stage, which is 43 dB, and 100 is the gain on the second stage, which is 40. So 40 plus 43 is 83, and the corner frequency is going to be around 80 dB gain, so 3 dB down. So it can be used up to 80.6, somewhere over here. So it can be used up to 2 megahertz as the 3-stage op-amp frequency. This frequency remains the same, and here I'm going to put in phase, and the phase I'll put a unwrap. Okay, unwrap, bracket open and bracket close. Okay, so now this one I can put on the right axis. Why is it okay? 180 degrees, of course it will be 180 degrees. So let's put it on the right axis, and let's make it thicker. Okay, so now let me check at 0 crossing what is the margin, because 180 you have already lost, right? So if I put here a marker, so this is going to be so okay, so I don't have a, so over here 180, so I have rolled back 180 and beyond that, so this is not stable, right? Then I would have to stabilize this, right? So to stabilize this, okay, this is a differential. This is a differential stage, right? And this is a 2-stage. You will roll 180 on this and you will roll on this. So really you cannot even say on the margins. So we cannot talk about margins because we are not going to use it in a feedback. Okay, so I'm going to drop this idea. If there is some inputs, please let me know. But I think that we will not be looking at, because we will anyway roll off, right? And this I'm not going to use in any feedback mechanism, right? So okay, so now this is the story for a instrumentation amplifier 1. Now I'm going to copy this cell as instrumentation amplifier 2. Copy cell. Okay, so I will copy this as instrumentation amplifier 2, right? And over here I am going to replace it with OTA 2C, right? So that would replace here. So I'm going to delete all these. Okay, I might not need the current source, so that goes off. So this one goes off and this one goes off. Okay, non-inverting, inverting. Okay, fine. Okay, so this is connected and we have a ground here, and we have a VDD here. Fine. So next I am going to copy this and copy this one and mirror it out and put it here, and F5 over here, and then I will copy this guy and put it at the output stage like this. So now the same thing is repeated with the OTA. Right? Okay. So now I have got 68 dB gain, and I have to go up to 65 as a corner frequency. So this is over here. So I have 32 megahertz first corner frequency. Then this one should be okay in the phase, because this is a single stage, right? So I will still plot the phase, though I'm not sure if it makes sense in the case of cascaded amplifiers. So I will say unwrap something. So now this is a two stage, because each one is a single stage, right? So let's put it on the right hand side axis, and I will still try to find out what is happening to at zero crossover. Okay, so this is 180. So this is 180 degrees. This rolls off at the zero crossing. So unless I use it in the feedback thing, they are almost looking the same, right? So this won't make a sense. Okay, so this is the situation in case of this thing based on OTAs. Now I'm trying to wonder why I'm losing the gain. So if I go inside, I have an output stage which can deliver current, right? So if this can deliver current, then this should be just a function of these resistances, right? So it should give a 80 dB gain, while it is not giving a 80 dB gain unless the gain of each one is messed up. And what is going to mess up is the current drawn from this node. So if it is a follower, it should not have a problem, right? Okay, so this is an open-ended question which I leave to the audience. They can put a remark. Okay, first thing they should put a remark is, if I was to use the instrumentation amplifier, should I be looking at the phase margin? That's the first question. Second question I still have is, why did the gain with the OTA go down? So please write your suggestions. At present I'm not thinking into it. I'm just doing it on the fly along with you. So I have don't have a prepared answer for that question. Okay, so I'm going to stop here in this session, and thanks a lot.